hopefully we'll get into chapter 3 as well. And I see most of you have put here in the chat box as perfect for the role. So where we sort of left off was last time we really sort of finished up talking about electron configuration, how to write electron configuration for sort of our representative elements and also our transition metals. And we really did sort of tie it in with the quantum numbers that we were talking about. And again, as we saw, as we went through several of those sort of examples, you really can, get really specific in terms of the quantum numbers, your N number, your L number, your M sub L, and your M sub S, right down to the specific sort of electron that you're talking about. And you can write it for those guys. We saw the order at which you want to write electron configuration. And again, that's that thing that you could kind of create pretty easily on a piece of paper, the kind of zigzag sort of way of doing it. And with that, it'll give you the correct order, remembering that pretty much the S and the D is sort of where we have a normal sort of change. So remember, for example, it goes into the 4S first and then back to the 3D, and then it continues on sort of in that pattern. And that really has to do with sort of our transition metals, which have D electrons in them. And our transition metals will, again, have 4S2, for example, in that first period, 3D something. And when we do lose electrons, for example, or gain electrons for our representative elements, as we saw, they essentially end up in the noble gas configuration. So that's sort of the whole basis of bonding, which we'll talk about in the next chapter. Pretty much everybody wants to get to that noble gas configuration. So in the terms of metals and non-metals, when they come together, metals typically will lose electrons and they will back up to the noble gas that comes right before them. While non-metals, on the other hand, will gain electrons and essentially go forward to the noble gas that comes right after them. And that essentially means that they will either lose those electrons at the end of their configuration or gain the electrons in the end of their configuration to basically achieve that noble gas configuration. And when things do have sort of the same electron configuration as something else, that's what's known as being isoelectronic with each other. So for example, sodium is isoelectronic with neon. Sodium ion has 10 electrons, and obviously neon also has 10 electrons. So they both have the same electron configuration, and again, are said to be isoelectronic with each other. Now, remember that transition metals are slightly different, especially in the way that they lose electrons. When transition metals actually do lose electrons, they typically will lose their S electrons first. And that's because, as we talked about, when the electrons go into the atom, they do go into, for example, the 4S first, and then start filling the 3D. But what happens once the 3D starts to get some electrons, or those d orbitals get electrons, there's a switch in terms of the energy that occurs for those different subshells. And what ends up happening, for example, is the 4s orbital actually ends up being higher in energy than the 3d orbitals. And the result of that is when they go to lose electron transition metals, they will always lose the s electrons first. And then if they need more electrons, as we saw in a couple of examples, they will then dip into the d electrons to do that. And that follows suit for everybody in the transition metal region, which pretty much on the periodic table, that's our transition metals between group 3 and group 2. That's pretty much everybody in there would do that. In addition, there is a lot of sort of exceptions to the normal sort of electron configuration in terms of its order. And the two that we talked about that you do need to be responsible for is chromium and copper. So chromium at 24, copper at 29. The exception is the same for both of them. They both have one extra electron up in the d orbitals and one less electron in the s orbitals. And again, in the case of chromium, that gives it one electron in each of the d orbitals. In the case of copper, it kind of pairs up everybody in those d orbitals. Now, there was a number of other exceptions that we also saw, I think, on that slide. And again, as we talked about last time, if you go kind of below chromium and copper on the periodic table, you'll see a lot of exceptions, like very similar ones. So silver, for example, is an exception. And again, there's some that does not even have any s electrons. They've all been promoted upwards. they're able to promote upwards because essentially they're super close in energy, and even with that sort of exchange of energy that happens with those orbitals, it doesn't take a lot for sort of an electron to be able to kind of bounce up, for example, into the d orbitals in terms of stability. So I think that's mostly what we talked about last time. Any questions on any of that before we kind of hopefully finish up the rest of this chapter that I can help anybody with? Okay. So we're going to talk about the periodic table and then really periodic trends to kind of end this chapter. So I added a few slides. They're basically a periodic table, so we had something to look at rather than me kind of drawing a bad periodic table. So you won't have necessarily these slides, but it is essentially really just a periodic table and a couple of things that mainly we probably know what they are, but you could probably add in. And again, it'll be in the recording in case you want to look at it again. But let's talk officially sort of about the periodic table. Usually in class, I just point to the wall when we start talking about it, but we'll point to this, I guess, and so well. That is a periodic table, obviously, that we see there. And again, we're going to talk about some of the parts of the periodic table just to make sure, again, everybody's on sort of the same page in this. All the recordings are being posted in the module section. So if you go to the module section, it'll have one that says past recordings or past lectures, and that's where you can find them all. So let's take a look at the periodic table and talk a little bit about it. So obviously the periodic table is an arrangement of the elements, and there's a couple sort of terminologies that we use with the periodic table. So a column of elements going up and down, so going top to bottom there. Those are referred to as groups. You're super old like me, so I'll call it family sometimes, but nobody really calls that too much. Most people go with groups. And if you look at periodic tables, depending on the periodic table and when it's built, I guess, or made, there's some different numbering schemes that you see. And usually in most chemistry class, we usually use sort of the A numbering, if you will. And the A numbering is usually what is referred to as the representative numbering. And what that means is over here, this is group number 1 again. This is group 2. We skip all the middle part. This is group 3, 4, 5, 6, 7, and 8. Most people don't really call it 1A, 2A, and so forth. Most people just call it 1 through 8. A little note on this, group 1, although hydrogen is sitting there, it actually does start with lithium. So lithium actually is the first member of group 1. We'll talk why hydrogen's over there in just a second. But even though it is on most periodic tables on the left-hand side of their hydrogen, it is actually not part of group 1. So group 1 actually does start with lithium. Then we have group 2. Again, we skip the middle section, 3, 4, 5, 6, and 7, and 8. Going left to right on the periodic table, so heading left to right on the periodic table. These are what are known as periods. And as you can see, there is 1, 2, 3, 4, 5, 6, 7 periods going down. And that relates to, as we talked about, I think, with electron configuration, that you literally can count off the electron configuration on the periodic table where the periods represent the n number. So period 1 going across would be n equals 1, n equals 2, all the way to 7. Hence why we say that n has values of 1 through 7, because as you can see here on the periodic table, that takes care of pretty much every element that will come across in this situation. By those periods. So periods left to right on the periodic table, groups up and down, and we obviously have talked a number of times about the number that we see above the symbol on the periodic table. That again is the atomic number, and that is the number of protons there are in an atom. We saw that when we talked about atomic number, mass number, protons, electrons, and neutrons. On the bottom of the symbol, as you can see on this periodic table, is what is known as the atomic mass. Again, as we talked about at that point as well, it is not the mass number, but it is the atomic mass, which is basically the weight of an atom based on protons, electrons, and neutrons. The periodic table really is broken apart into 3 sort of categories. There is metals, nonmetals, and semi-metals. And usually on most periodic tables, as you can kind of see here, there's usually like this sort of staircase that's happening. And usually to the left there of the staircase, those guys are all metals. And metals are really good conductors of heat and electricity. They're also malleable. You could hit them into sheets, pull them into wires. They're very shiny as well. And for the most part, all of the metals are pretty much solids at room temperature. The one exception is mercury. And mercury is actually a liquid at room temperature. And mercury is approximately right about here on the periodic table. So mercury is just a liquid. All the other metals are pretty much solids. And on a lot of periodic tables, you oftentimes find mercury kind of in a different color. So a lot of times they'll put it in blue and stuff like that, just to represent that it is a liquid rather than a solid. And by the way, when we're talking about sort of these elements and stuff like that, if we do have something, and we talked about charge and things like that, if we do have something all by itself, for example, if I just had a piece of copper metal, the copper does not have a charge. So it would be just Cu, no charge written on it or anything like that. Things, again, only get charges when they start to bind, and really ionic bonding is happening when the metal and the non-metal come together. That's really when things have charges. So if you just pulled any sort of element off the periodic table, it would not have a charge. It's pretty much neutral in that sense. Non-metals, as you can see, are really to the upper right of the periodic table. The upper right of the periodic table, just left the periodic table. Upper right of the staircase there is our non-metals. Also, in terms of metals, not on this one, but at the very bottom, there's like 2 rows, as we'll see later. Those guys are also metals on the very, very bottom. Those 2 kind of rows that are by themselves, they are also metals. Now, non-metals are pretty much the opposite of metals. They are bad conductors of heat and electricity. They have a more varied sort of state. So some non-metals are gases, some are liquids, and some are solids. And a lot of the non-metals that we come across are those diatomic molecules. So remember, diatomic molecules are those guys that have 2 atoms. So a lot of those elements that are non-metals, they do come as these diatomic molecules, are guys like this, right? Now, the reason why, again, right here is hydrogen on the periodic table. The reason why I said earlier that hydrogen is not part of group 1 is because group 1 really contains metals. And as you can see from the coloring here, although hydrogen is hanging out over there with our metals, hydrogen is actually a non-metal. So hydrogen is a non-metal, even though on pretty much every periodic table you ever see, it will be over there in the metal region. Years ago, older periodic tables used to actually put hydrogen on both sides. So you sometimes see hydrogen written on both sides. They don't do that too often anymore, probably because people are confused, like there's 2 hydrogens. But you'll usually see that hydrogen over there on the left-hand side above lithium. So this is really lithium right here. And again, as you can see here, lithium is a metal, hydrogen is a non-metal. So again, when we talk about group 1, it does start with lithium here because hydrogen really is a non-metal. Now, when we hydrogen is really not in a group. It's not really considered any part of a group. It's just sort of by itself. It's really not a member of group 1, even though, again, on pretty much most periodic tables, you'll see it right on top of it. Again, group 1 really does start with lithium. So in that sense, hydrogen is really not necessarily part of a group. Hydrogen has some unusual sort of characteristics. One of those things, for example, it can be positive, it can be negative. Also, hydrogen is the only element that has a proton and an electron and no neutrons. So again, everybody else has neutrons except for hydrogen and stuff like that. So technically speaking, hydrogen is really not part of any group. And it has a lot of sort of special properties, which again is why years ago they used to kind of put it on both sides, because they're like, it is really a non-metal, so it should be over here. But it does a lot of things similar, I guess is the way to put it that way. It does a lot of things similar to members of group 1 in terms of losing electrons. So hydrogen will typically lose 1 electron, very much like everybody there in group 1. So has a lot of similar type properties in that sense as to some of the members of group 1, which is again why it's probably over there. And again, years ago, they used to kind of put it on both sides. So the other part here of the periodic table, or what are known as metalloids or semi-metals. I think most people now go with metalloids, not so much semi-metals. And it's sort of this staircase that sort of comes down here in blue. And you can see on this periodic table, they also include boron, which is here. I'm trying to remember off the top of my head if your book does or not. I don't remember. Sometimes they'll include it or not include it. Boron, a lot of times in terms of naming and things like that, are thought of almost like a non-metal. So a lot of people just kind of put it into a non-metal sort of category. But some periodic tables, as you can see, like the one on top there, does include boron and stuff like that. But this sort of staircases are metalloids. And really what metalloids are is, if you just think about sort of their location on the periodic table, all these guys are metals. And then as you sort of head upwards this way, we're getting into non-metals. So these guys in the metalloid region are elements that have properties that are both properties that are very similar to metals, and the same element will have properties that are very similar to non-metal. So they sort of are on both sides of the fence, if you will. The same element has some properties that normally would be classified as definitely metal type properties, while as you go to the other side there, that same element will also have some properties that are very similar to non-metals. So a lot of semiconductors, for example, are sort of in that region. And so we have sort of that transition that occurs, if you will, going from metals to our non-metals, upper right of the periodic table. Now, some of these groups do have special names, and you do need to know them. So starting over here, again with lithium, not hydrogen, is group number 1, and group number 1 are the alkali metals. So group 1, which is lithium, sodium, potassium, rubidium, cesium, and all those guys, francium, those guys are what are referred to as group 1, are the alkali metals. Again, hydrogen not part of that group. Going right next door to group number 2, starting here with beryllium, that is our alkaline earth metals. And when you think about the word alkaline, for example, alkaline pretty much means basic. And if you think about the sort of members there of group 1 and 2, that's where a lot of strong bases come from. So there's things like sodium hydroxide, potassium hydroxide, calcium hydroxide. So a lot of these guys here, when they hook up with OH, make a lot of strong bases. And that's sort of the root of where those names come from: alkali, alkaline. And again, if somebody says make it alkaline, you'll come across that a lot in Chem 200B. And when you do some experiments, they say, hey, make the solution alkaline. And basically, that's what it means to make it basic, is essentially that. Skipping all the way across over here to group number 7, which is our fluorine, our chlorine, our bromines, our iodines. These are all really a lot of those diatomic molecules. Those guys are what are known as the halogens. So the halogens is group 7 on the periodic table. And again, our fluorine, chlorine, bromine, iodine are members of them. And our last sort of important group here goes right next door, up here with helium and down. That is our noble gases. So group number 8 is our noble gases, as we'll see in just a second. But basically, noble gases are sometimes referred to as being chemically inert, which means they're not very reactive. They don't react with a lot of other things. They'll react with themselves, but they're not very reactive. They're kind of really stable as well. And as we sort of talked a little bit about last time and at the beginning here today as well, you know, that's ultimately sort of the goal of bonding, is for everybody to end up with the same electron configuration as group 8. And again, that's because they are so stable and they're really happy just the way they are. And that's sort of the ultimate goal there of bonding, both ionic bonding, covalent bonding, is for everybody to be just like the noble gases. Again, sort of a very, very stable situation. And that's sort of the goal there. Oops, come back. Cool. And in addition to our noble gases, as I just mentioned, there are these two rows at the bottom of the periodic table. And again, if you sort of count the numbering here, we go from 56 to 57 and then 72. So this guy right here, which is 58, technically should go right about there. And this guy right here, 89, 104, here's number 90, which technically should go right about there. So technically these two rows here that are set out at the bottom should technically go right about there on the periodic table. And they are sometimes referred to as lanthanides and actinides, and that's because those are really the two elements that they follow on the periodic table. And they're set apart so that the periodic table wouldn't be so wide. It'll never fit in the cover of a book. I've only seen once where they put those guys in the right location and they need an entire wall to put the periodic table up because it spread it out so wide. Looking between group number 2, which is here, and group number 3, which is here, right here is our transition metals. So these guys are our transition metals. And we talked a little bit about some properties there. And as you may know as well, transition metals in terms of charges are the guys that typically will have a variety of charges. So they have variable type charges. And that is, again, basically that 21 to 30 and down is all the transition metals. And that is why these two rows down here, which technically go right into here, these guys are also sometimes called the inner transition metals. And that's because technically they should be hanging out right about there where the transition metals are. Most people don't do too much with those guys. And in this class, we also won't do too much with them. A lot of those guys on the bottom two rows are a lot of radioactive elements. You know, you should know uranium probably, which is 92. That one does come up a lot, but you probably won't see too much of these guys. Maybe when you take 200B and talk about nuclear chemistry in that class there, you'll touch on some of these. This part of the periodic table, and you may see some different sort of symbols, and you know, this part of the periodic table, it may not see so many symbols at all in that part of the periodic table, depending on sort of when your periodic table was sort of made. That part of the periodic table that I sort of circled there is typically the part where they kind of place elements they haven't fully decided are going to be classified as elements. So like that's why they have some of these weird symbols, like some U, whatever it is on this particular periodic table. So those are ones where they haven't fully decided that we're going to be official sort of symbols. So on some periodic tables, you may not even see some of those symbols in that area, and you may see some other symbols in that area as well. So there's sort of a variety of things you may see in that location on the periodic table, again, depending on sort of when your periodic table was printed as to sort of what was going on at that point. Any questions on sort of the periodic table, the organization? You need to know, obviously, where metals, nonmetals, and metalloids are. You need to know which way groups go and the proper numbering of groups 1 through 8. You need to know which way periods go and where periods 1 through 7 would be. And you need to know, obviously, the special names of those spots, the alkali metals, where that is, alkaline earth metals, halogens, noble gases, and obviously the transition metals. Any questions on the periodic table or anything like that? Yeah, there will be, you will be given a periodic table on exams and quizzes if you need it. The periodic table will contain pretty similar to what you see on the screen. It will have the symbol, it will have the atomic number, and it will have the atomic mass. It will not have any like names or anything like that. So you obviously, hopefully you know most of the name symbols, but it will be part of the exam. Other questions? Okay. So now we sort of officially talked about the periodic table. Let's talk about periodic trends and some trends that we see on the periodic table that helps us understand sort of what happens with certain elements, and especially what happens when certain elements sort of get together for bonding and stuff like that. So let's take a look at that. So this should hopefully pick back up on your notes at this point. So we're going to look at several different sort of trends on the periodic table. We're going to look at ionization energy, what it is. We will also look at electron affinity, atomic radius, and we're going to also add into there another trend, which is known as electronegativity. And electronegativity is actually from chapter 3. So if you look at sort of the syllabus and the schedule and all that, it will say like exam 1 is chapters 1 through 2 and chapter 3 point, I almost want to say 2 or 12 or something like that. And so this is the only thing technically out of chapter 3 that you'll need to know for the first exam. We will go more into it when we get to chapter 3. But you just need to know what it is, and we're going to talk about in a second what it is and sort of the trend for the first exam. And then in chapter 3, when we officially get there and get to it, we'll talk about it in terms of bonding and stuff like that for exam 2. So it does say like exam 1 is chapter 1, 2, and 3 point something. The electronegativity part is the 3 point something that you need to know for the first exam. So let's talk about a couple of things. Let's first talk about one type of property of atoms, which is sometimes referred to as effective nuclear charge. An effective nuclear charge, which is sometimes referred to as Z effective, is what it's referred to, is sort of the positive charge that, for example, electrons feel as a result of something that's referred to as shielding. So let's just say, for example, we had a nucleus that had 3 protons. So that 3 protons would give that nucleus a positive 3 charge. And in this atom, we would have a couple of electrons in, say, the first energy level. We'll have a couple in the, or one in the second energy level. And when we look at something like this, for example, these electrons here, which are closer to the nucleus, sometimes referred to as the core electrons, are definitely closer to the nucleus here, which means that these electrons are going to feel really the full brunt of that positive 3 charge. And one sort of important thing to keep in mind is we talked about the idea of opposites attract, right? So things that are positively charged, things that are negatively charged, which is known as electrostatic attraction, are attracted to each other. Now, the strength of that attraction increases with the size of it. So for example, something with a +3 charge and a -3 charge are really attracted to each other, and they would be strongly attracted to each other or stronger attracted to each other than something with, say, a +3 charge and a -1 charge. So it won't be held as tightly, or a -1 and a +1 type charge. So the sort of magnitude of the charge, you know, is important in terms of the strength of that attraction. Now, when we look at this third electron here, which, by the way, if we sort of wrote up the electron configuration here, 1s2, 2s1 in this case, again, these being our core electrons, our electrons over here, which are in the highest energy level, this being our valence electron. This guy here is experiencing what is referred to as shielding. And what that means is that electron, that third electron there, because it's at a higher energy level, is shielded from the full effect of that positive charge that we see in the nucleus. It's kind of like when you're in the movie theater, or years ago when they didn't assign seats, right? You go, you sit, they get there early, sit smack dab in the middle of the theater, and it's like right before, you know, the movie starts, somebody comes in with the big giant cowboy hat, sits in front of you, and you just lost half of your screen. You've just been shielded from the screen, right? And it's sort of the same idea here. These electrons in the front row feel the full brunt of that positive 3 charge, but they are sort of screened. This last electron is screened from that charge by these 2 electrons. And you could calculate the Z effective, which is the effective nuclear charge of that electron, by taking the positive charge and adding it to how many electrons are screening it, which are 2. So that's like a -2, -1 for each electron. And what that essentially tells us is this electron over here, that third electron, is only feeling like a positive one attraction to that nucleus, which obviously means it is not going to be held as tightly as those core electrons, which are closer to the nucleus. And that is why, for example, when something like this, which by the way is lithium, when lithium loses an electron, it is this one that comes off because it's not being held as tightly and it's easier to remove in that case. And that's why lithium, when it does make a charge, makes a positive one charge, because this one can be popped off relatively easy. And part of the reason for that is this idea of shielding an effective nuclear charge. Again, just because of its distance from the nucleus, is not feeling the full brunt there of that positive charge and not going to be held as tightly. It's kind of obviously like if you have a magnet, right? If you keep the magnet kind of really far away from something or relatively far from something, you know, you could kind of see the object move towards the magnet. Obviously, if you move the magnet way close to it, right, it just jumps right onto it. There's a lot more of attraction that's happening there. And it's sort of the same idea here. Because of the distance, because of those electrons sort of in the way, those outer electrons don't feel as much of a positive charge or attraction to the nucleus as those electrons which are closer up. And that's why when we talk about losing electrons, it is always those valence electrons that get lost because of their distance from the nucleus. Any questions on that there? Okay, then let's talk about really what ionization energy is. And since we're talking about losing electrons, when we do lose electrons, as we talked about, that is when we do form ions. And the ions that we form are what are referred to as cations, right? And typically it is the metals that will lose electrons and form those cations, which are positively charged. And the energy that's required to remove an electron from the gas phase of an atom is what's known as the ionization energy. And the ionization energy is just that, the energy to remove one electron. So electrons actually do come off one at a time. So sometimes we think about, oh, this guy makes a +2 charge, it just drops 2 electrons right away and it makes that charge. But it actually does lose electrons one step at a time. And we can see that, for example, in magnesium here, magnesium with no charge. The first thing that will happen is it will lose 1 electron and become positively 1 charge. The energy required to do that is what is sometimes referred to as the first ionization energy. And that is the energy that's required to remove the first electron. Then what happens is this magnesium that now has a positive 1 charge will lose 1 more electron. And the energy required to do that is what is known as the second ionization energy. And then this magnesium would potentially have to lose 1 more electron to become positively 3 charged. And that is what is known as the third ionization energy. And the thing that we could see is as we continue to lose electrons here, we see that the ionization energy increases. So the first ionization energy to the second ionization energy to the third ionization energy to however many ionization energies you may have, it tends to increase. And the reason for that is, if you just think about it, when we lose an electron, the overall electron cloud shrinks. So all the electrons sort of come in, and the size of a cation is smaller than its neutral counterpart. So a cation is typically smaller than its neutral guy. And that's because as it loses electrons, that electron cloud basically starts to decrease and the overall size starts to shrink as a result of that. What that means is a couple of things. Now, even those outside electrons, because you lost that 1 electron, those outer electrons have now moved closer to that positive charge and they're going to be held tighter. So it takes more energy to remove that second electron. And that's what we see here. It takes 735 kilojoules to remove the first electron of magnesium. It then takes 1445 kilojoules to lose that second electron, almost double the amount of energy. So the question is, why is there a plus sign if magnesium is losing an electron? Are you talking about this plus here? When it loses an electron, the element then has more protons, which are positively charged than electrons. So that's why it becomes positively charged when you lose an electron. If you're talking about the plus sign here, this is just if you're talking about that plus sign, that is a way to represent that something has lost an electron. So it's almost like a chemical reaction to demonstrate that this magnesium has lost an electron, basically gave it off. So that's why that plus is there. That's the one you're talking about. It's basically to indicate that the electrons being given off. And it really has to do with sort of everything being balanced, right? The overall charge over here is 0. +1 and -1 gives you 0 on the right-hand side. So everything's balanced in that sense, if that's the plus sign you're referring to. You're welcome. So once we lose that, for example, second electron there, we see that, oh my, it goes up like almost 7-fold if you want to try to pull off one more electron. And that probably is not going to happen because that's a lot of energy. And if we think about magnesium, it is 1s2, 2s2, 2p6, 3s2. And in terms of magnesium, these two guys here are valence electrons. And then when we get down into here, we're starting to get into our core electrons. So those are the electrons that started out closer to the nucleus. And as we start losing the electrons, they're going to get even closer to the nucleus at this point, right? So they're all going to kind of come in. And we typically don't lose those core electrons. And that's why when we think about something like magnesium, it normally is a +2 charge because it's group number 2. And that's normally what it makes. And again, you typically are not able to sort of remove core electrons. Again, they're just really tight in there. Also, if you just kind of think about what happens at that point, we've got rid of those kind of 2 electrons which are higher, and then we have all 6 of those electrons in the p orbitals there, all in the same energy. There's really no kind of shielding happening at this point, and they're all just going to continuously sort of increase down into the nucleus and be held a lot tighter. So in general, when we kind of look at ionization energy and we look at the periodic table, what we see in terms of the trend on the periodic table, maybe I'll go back here to draw something maybe. So on the periodic table, if we just sort of draw a periodic table here, ionization energy increases as you go this way on the periodic table, and it decreases as you go this way on the periodic table. So upper right of the periodic table has the highest ionization energy. And again, the increase in ionization energy means it's much harder to remove an electron. The lower the ionization energy, the easier it is to remove an electron. Yeah, so typically it's usually those valence electrons that are being shielded. In reality, the ones below it are also being shielded a little bit by the ones in the level below them. So, for example, electrons in the first energy level kind of shield the ones in the second, and those guys kind of shield the ones in the third, and so forth. But usually in terms of shielding, we sort of look at it in terms of the ones below them. Now, if you have electrons on the same energy level, they won't shield each other. So for example, if we had those 2 electrons, those 2 outer electrons there in the same energy level, they won't shield each other, but they are shielded by any electrons that sort of come below them that are closer to the nucleus. So that's an important trend to know. The ionization energy, again, to the right and up on the periodic table increases, to the left and down decreases on the periodic table there. So in general, as we go across the period left to right, the first ionization energy increases. So electrons are added to the same principal quantum, do not completely shield the increasing nuclear charge caused by protons. So remember that as you go left, right on the periodic table, if you just look at the atomic number, it starts to increase. The increase in atomic number means more protons. More protons means everybody's going to be pulled in tighter to begin with. And electrons in the same principal quantum level are generally more strongly bound from left to right on the periodic table because of that. Now, in general, as we go down a group on the periodic table, again, we see the ionization energy increase. So in addition to that greater positive charge that's happening, it also will have more electrons. So more electrons as you go left and sort of down on the periodic table, greater electrons further away from the nucleus, more shielding happening, not going to be pulled as tight. And we will see them being a little bit less held on in terms of the ionization energy. So here's just sort of the trend in ionization energy as you kind of go across the periodic table there. This is helium, neon, argon, krypton. That's group 8 on top. And the general trend, as you can see, is starting to decrease as you kind of go downward on the periodic table. And again, that's related to group number 8, right? As we sort of go down this way, ionization energy starts to decrease, and we sort of see that trend. So in general, ionization energy decreases as you go down and to the left on the periodic table, and it increases as you go up and to the right on the periodic table. So this way, whoops, bad line there. We'll go that way. Increases, decreases as you go down. So that means if you happen to be in this group and you're heading down, in that group it should decrease. And then obviously in a period as you go left to right, it should increase as I go that way. So explain why the graph of ionization energy is not really linear. Again, there is some repulsion and some exceptions that basically occur. You don't have to worry about too much of those exceptions or anything like that. But ultimately, we do have some electrons near electrons. So there's going to be some repulsion that occurs between those guys in the same energy level. They don't really like to be near each other. But the general trend is what I just told you, up and to the right on the periodic table, increase in ionization energy, and left and down on the periodic table, we have a decrease in the ionization energy. So take a second here. Which one would require more energy to remove an electron and why? Sodium or chlorine?
So I think it would have to be chlorine.
Yeah, it would be chlorine. So in this case, if you just think about the locations here, we have sodium on this end, we got chlorine on this end. So remember, increases ionization energy as we go this way. And you would be correct. It is chlorine here in terms of the one that should be more energy to remove it. Again, because as well, when we go to the right, we have greater positive charge, bringing those electrons in. And again, even the furthest out electrons are going to be closer to the nucleus and going to be held tighter than if you go to the left, where the sizes we'll talk about in just a second, a little bit larger in size because it has a less of a positive charge. So those outer electrons are going to be a little further away and not be held as tightly. So yeah, you are correct there. Chlorine should be the one that has more energy. In terms of lithium and cesium, and this one, what do we think? This one The one that should require more energy is, it should be in this case, if we look at lithium and cesium, they're actually in the same group. Lithium's here, cesium's down there at the bottom. So we should expect lithium, right, to require more energy. Again here, they're in the same sort of group on the periodic table. Lithium here with his +3 charge and only 3 electrons, again going to pull that in tighter. And this guy is going to have his outer electrons a little further away. So it's going to be easier to remove those electrons and less energy to do so. Any questions on that too there?
I'm sorry, could you re-explain the concept that like it's held in tighter as we go down? Just the going down part is not.
Yeah, so in general, in terms of the periodic table, we'll talk about it here in just a second, but here it's just kind of preview. So in terms of size of atoms, right? As we go to the right on the periodic table, everybody gets smaller, right? In terms of just the overall size of atoms. And as we go down, we get larger. And the reason for sort of that idea is, you know, as we stay within a period going left to right, we see an increase in the positive charge, right, buildup of those protons as you go left to right on the periodic table. And the buildup of those protons are going to bring those electrons in closer, and it's going to be smaller. Again, because as we build up the positive charge here, we have not a heck of a lot of electrons as well as you go to the right. You get down here, you also have a buildup of positive charge. You know, that's a bigger atomic number as you go down, but it also has a lot more electrons. So there's a lot more electrons in the way, doing a lot more shielding going on, right? So these outer electrons, you know, by the time they kind of feel anything from that positive charge, they're going to be not a very high attraction. So they're going to find themselves able to, badly drawn here, kind of be able to float away a little bit further from the nucleus than say somebody over here, because there's not as many electrons in the way. So even those outer electrons are still going to feel a pretty good positive charge as you go up or right on the periodic table, and that's going to bring everybody in. And that's why overall it gets smaller the size as you go up or right on the periodic table. And as you go left and down, even though you have that bigger positive charge, you also have a lot more electrons in the way. And that's going to allow those outer electrons to not feel as much of an attraction and kind of be able to kind of float away, bringing the overall size of the atom being a little bit bigger. And what that translates in terms of ionization energy, again, is because these electrons are so much closer to the positive charge nucleus, they're held tighter, takes a lot more energy if you want to try to remove them. And that's why we see an increase in ionization energy, as opposed to over here, as we were talking about, sort of these outer electrons, they got enough sort of lag, if you will, that they could kind of float away. They're not being held really tightly because of all the other electrons in their way. And it takes a lot less in terms of ionization energy, or a lot less energy to remove those outer electrons in that case. Questions on that? Yeah? Other questions on that? Yeah, so that's sort of the idea. Again, you kind of think about there's an increase in positive charge kind of both ways you go, right and down. But the difference is as you go to the right within a period, you don't have such an increase in the amount of electrons that are also there. And again, as you go left and down on the periodic table, in addition to that positive charge increase, you also have a lot more electrons sort of in the way of, and also shielding those outer electrons, that they're not going to be held as tightly because of that. Other questions on that? And that's the case here with lithium and cesium. Again, even though you may think, well, this guy has a much bigger positive charge, he also has a lot more electrons in the way. So cesium's all the way down there in the 6s1 range. So it's got a lot of electrons happening, you know, in front of this kind of one electron, and going to cause a lot more shielding. Also the 6th energy level, which is way away from the nucleus, right? As opposed to lithium, which is 1s2, 2s1. Our most furthest electron is only in the 2nd energy level, right? And that obviously is much, much closer to the nucleus than somebody in the 6th energy level with all those electrons in the way. other questions on that? Okay. So which would have the larger second ionization energy? Would it be lithium or beryllium here?
Lithium?
Lithium does sound right. Yes, it would actually be lithium. That is the right answer. So let's talk about why that is the right answer. And we could just really look at the electron configuration of each of these to sort of answer that. We have 1s2, 2s1, which is lithium, and beryllium, which is right next door at number 4, would be 1s2, 2s2, which is beryllium. Now, when lithium loses its first electron, right, and they both lose the first electron, actually both of these, right, that is our first ionization energy for that first electron to come off. So when lithium does that, and it does this move here, and when beryllium does that, and it loses its first electron, you may say, well, it looks pretty good to each other. So what's the deal with the second ionization energy? Second ionization energy would be lithium with a +1 charge dropping off another electron. And it would be beryllium here with a +1 charge dropping off another electron as well. So the correct answer actually is this one here, because when we look up here for lithium, lithium has 1 valence electron. Beryllium has 2 valence electrons. And if you remember, the valence electrons are the electrons in the highest energy level. They're the ones furthest away. And if you remember, I think we talked about last time as well, you essentially can use the group number to figure out the number of valence electrons. So when lithium loses its first electron here, it now would have to go into its core electrons, which these electrons are super close to the nucleus, going to be held really tight and probably not going to happen. But when beryllium loses that first electron, he still has 1 more valence electron to go. And that means that's not a problem for him, because he technically can lose 2 electrons with no problem. And that's why the ionization energy here for beryllium's second one should actually be lower than lithium's, because this is probably not going to happen, because you're going to be starting delving into your core electrons, and it would be an incredibly amount of energy to do that. And you don't usually jump into those core electrons and lose it. So you were correct there. Good answer. Lithium is the correct answer, again, because once it loses that first electron, the second electron, which would be where your second ionization energy would come into play, will now get you into your core electrons. And it's probably not going to happen in terms of lithium. It takes a lot more energy to do that. And again, doesn't take that much energy more for beryllium, because you're dealing with the second electron still being a valence electron furthest away from the nucleus, not really being held as tightly and able to basically be removed. Any questions on that one? So here is sort of a chart of that, and what you see is what we've been talking about. This is the first ionization energy, second, all the way across. Again, each of these represents basically 1 electron coming off at a time. So the first ionization energy, that first electron loss, second one, third, and so forth. So when you look at something like sodium, for example, which is group number 1, and as we talked about, just to make sure, group 1, right, everybody has a +1 charge. Group number 2 on the periodic table, +2 charge. Group 3, which is aluminum, +3 charge. Group 4, no real good sort of path. Group 5, -3. Those are the nonmetals. Group 6 is -2. And group 7 is -1. Again, these guys being our nonmetals on the periodic table. It does increase. That's a good question. So the question was, when somebody loses the second valence electron, for example, like beryllium, is it the same amount of energy, or is it more? It actually is more. And again, it's for that same reason. Once it loses that first electron, the overall electron count is going to get smaller. So the overall size of that cations can get smaller, which means that second valence electron, even though it's further away from the nucleus, will now find itself moving closer to the nucleus after that first electron is lost. So it is going to be held at tighter than, it was when they both were there. And it will cause a slight increase in the amount of energy to do so. The actual number, I don't know off the top of my head, but you would see a general increase. And that's a general trend for ionization energy. As you can see on this table, the first ionization energy is usually smallest, and then the second gets a little bit larger, the third gets larger in terms of the value, and so forth. And that's what you kind of see here. This is the first ionization energy for sodium, which is 495, 4,560 kilojoules of energy needed to remove a second electron in sodium. That's like almost a 10-fold increase in energy that's needed to pop off that second electron. Doesn't usually happen, again, because that is your core electron for sodium. Sodium has one valence electron because it's group number 1. So once it loses that, you now have those electrons closer to the nucleus, held tighter, can't really remove those core electrons. This may answer your question that you were just asking. For example, magnesium here, 735 for the first electron. Its second valence electron, 1400. So almost a double increase in terms of the amount of energy to remove that second electron. And then at that point, you can see it gets almost 7 times the amount, or 10 times the energy from the first one to remove that third electron. Again, doesn't happen. And again, you see the sort of the same path as we go this way. An increase in ionization energy from first to second to third. And overall, once you sort of hit those core electrons, past the valence electrons, not going to probably have enough energy in a normal situation to get those things to lose electrons. And that's why, for example, when you look at something like sodium, we never typically see sodium with like a +2 charge or +3 charge, because you're delving way into those core electrons, and it just takes way too much energy for that to happen, and just doesn't happen. So much so you don't even see numbers or anything like here, like we could keep popping off, possibly stuff like that. And usually what you'll see is sort of that first number into the core electrons, but usually it will not happen under normal conditions. Question on ionization energy. So when we think about ionization energy, we've sort of been talking about it in the sense of losing electrons and cation formation. So another important trend is what is known as electron affinity. And electron affinity is sort of the energy change that occurs when an atom gains an electron. So ionization energy is oftentimes thought of in terms of the formation of cations or positively charged ions. Electron affinity can be thought of as what happens when we make anions, which are our negatively charged guys. So anions, which is our negatively charged ions, and as a result of gaining electrons, is sort of what we think about with electron affinity. So in general, if you have an affinity for something, that means you like it, right? So if you have electron affinity, that means that essentially something does like electrons. And it's basically the energy change associated with gaining an electron in the gas phase. So when you make something, for example, like sodium chloride, like a sodium chloride solution, and you think about sodium chloride, we think about it in terms of, I got a solid sodium chloride or salt, right? I add some water to my salt. It goes directly from the solid to the liquid or the aqueous solution, right? It just dissolves, goes from solid to aqueous. What actually happens when you make something, for example, like a sodium chloride solution is, it's actually a two-step process. The first thing that actually happens is the sodium will lose electrons and the chlorine will gain electrons, and they actually will go into the gas phase. So those guys will actually go into the gas phase and go from sort of the solid phase to the gas phase. And then those guys will get hydrated. And as they get hydrated with the water part, when you're dissolving it, that is when they sort of gain and lose those electrons. Although we don't necessarily always see like, oh, I just made gas, and sodium gas and chlorine gas, which is good because, chlorine gas not so good for us. But it actually does happen sort of in a two-step process where they sort of gain those electrons in the gas phase or lose the electrons in the gas phase. So that's why we talk about gaining and losing electrons in the gas phase, because that's actually sort of when it happens. Although it happens so sort of quickly, we don't actually visually sort of see it, but that's sort of the process that occurs. And that's this representation here. So for example, if I had chlorine and it gained an electron, Cl minus, so reality, I should probably balance it. I'll do it this way. There you go. So this is basically chlorine plus 2 electrons. So what we see here is electrons on the reactant side or the left-hand side of the arrow when somebody gains electrons. And just a reminder that that is different than what we saw when somebody lost electrons, like sodium. When it lost electrons, what we see is electron on the product side or the right-hand side of the arrow when we lose electrons. Yeah. So this is a way sort of equation-wise or reaction-wise that this is sort of represented. And if you ever see an equation written where electrons are on the left-hand side of the arrow, which is the reactant side, that implies that that thing is gaining electrons. And if you see electrons written on the right-hand side of the arrow, like we saw in the previous examples, that indicates that they are losing electrons, like they're being given off. So that's just a way sort of equation-wise that we sometimes will represent what is happening with our electrons. So in general, the general trend, and it's not a perfect trend, but in general, when we talk about electron affinity on the periodic table, and again, not 100% perfect the way it goes, but up and to the right, it increases. So electron affinity increases up and to the right and decreases left and down. So electron affinity is different than electronegativity. We'll talk about what that is in just a second. But electron affinity is actually the energy change that occurs when somebody gains an electron. And we sort of got to this a second ago, but just to officially talk about it, the atomic radius or size of an atom, it does decrease as you go up and to the right on the periodic table and increases as you go left and down. So for some of the reasons we've been talking about, as you go up and to the right on the periodic table, again, you have sort of a greater positive charge, not as many electrons. So everything gets really compact in there as those electrons are attracted to the nucleus. So the overall size is relatively smaller, as opposed to when you go left and down on the periodic table, you have something with a lot more protons, but also a lot more electrons, which again is going to make those outer electrons being further away, and also a much bigger electron cloud, which just by that sense of it will be greater in size. So we talked about it the other minute ago that when we do form a cation, it is smaller than the neutral guy. And again, because it has lost electrons. When we form an anion, it's actually larger than its neutral counterpart. And that's for the same sort of idea. If we gain electrons, when we form an anion, we're building into that electron cloud. So we're putting more electrons in there and sort of building the overall size. And that's why oftentimes you will see when somebody draws something that's positive and negative together, you will see that the positive circle is typically smaller than the negative circle there. And it's usually larger because it's implying that it gained more electrons and became larger. Any questions with that there? And here's a nicer picture than I probably could draw in terms of that. And as you can see, as you go to the right and up, the size of everybody of our neutral guys gets smaller, left and down gets larger. Larger in size is what we're talking about, the actual size. So is sort of defined as sort of the atomic radius, so where the nucleus is, and sort of the how far it is in terms of the electron cloud, how far it goes. That's what we're talking about, sort of in terms of atomic size, larger in terms of that. And it does have an effect on things like density, which is mass over volume. And again, as you go to the right, you do have a lot more mass, but less volume because things are smaller. And the density and stuff like that's affected. It gets smaller typically as you go to the right and up as well. So here's a much nicer sort of picture, and one last sort of trend to add to all of our trends here, and we'll talk about why all that's important here. Again, is what is known as electronegativity. And this is the one thing from chapter 3, as I was talking about, that you do need to know. You need to know what electronegativity is. So electronegativity is the ability of an atom to bring electrons towards itself. And in general, on the periodic table, as you go up and to the right, it increases. Fluorine on the periodic table is the most electronegative element you could have. And as you go left and down, it decreases. So electronegativity and electron affinity, they are different things. Again, electronegativity is the ability of an atom to bring electrons to itself. Electron affinity is the actual change in energy that occurs when an atom gains an electron. So sometimes people kind of mix those two things together. They technically do sort of refer to different things, although it's kind of the same trend. So what does all these trends sort of mean when we think about the trends on the periodic table and stuff like that? Well, let's just kind of think about all the trends we've been talking about. So when we go up and to the right, we see that the ionization energy increases and it decreases as you go down. As we go up and to the right on the periodic table, the size gets smaller. And as you go down, it gets larger. As we go up and to the right on the periodic table in terms of electron affinity, I'll call that EA. Electron affinity increases up and to the right and decreases down and to the left. And lastly, what we just saw here with electronegativity also increases as you go up and decreases as you go down. So what all these trends tell us when we look at something on the periodic table is, if we go up and to the right on the periodic table, we have things that are small in size, which means that those outer electrons, even the outermost electrons, are going to be closer to the nucleus. That means that they're going to be held tighter, which means it's going to be very hard to remove electrons. And more importantly, because everything's so close to the nucleus, things feel a much stronger positive charge, which means not only is it going to hang on to its own electrons, it's going to want to grab some electrons from somebody else. And that's why when we think about the periodic table, up and to the right is where we find our nonmetals. And nonmetals are typically our guys that make anions and become negatively charged and gain electrons. For all of those trends, they're compact in terms of size. It takes a lot of energy to remove electrons, which typically doesn't happen. And they have very high electron affinity, which means they like electrons. And they have high electronegativity, which, in addition to liking electrons, they also have a very good attraction to bringing electrons towards themselves. And the opposite can be said if you go left and down on the periodic table. When you go left and down on the periodic table, the size of the atom is larger, which means the furthest out electrons are not going to be held as tightly, which means they have low ionization energy, which means it doesn't take a lot of convincing to allow them to lose electrons. In addition, they have very low electron affinity, which means they're not really looking to gain electrons. And they also have very low electronegativity, which means they're not looking to attract electrons to themselves. They much rather give away electrons. And that's why when we're on the periodic table, we go left and down. we have our metals, and they are typically our guys that will make cations and become positively charged. Question on sort of how those trends all work together, which sort of what we know. Metals lose electrons, positively charged. Non-metals gain electrons, become negatively charged. And if you had to venture a guess, the most active non-metal should be found on the periodic table. Where should we find the most active non-metal? Should be found up and to the right on the periodic table. And the most active metals should be found left and down on the periodic table. Again, based on those trends, that's going to give you your most active metal, left and down. Up and right would be your most active non-metal, because when you go to those extremes, you have basically those two extremes happening. Left and down, you got somebody that's going to be pretty willing to take my electrons, please. And when you go up and right, you're going to have somebody that says, thank you very much. I'll be happy to grab those for you and take those electrons and gain those electrons. Any questions on that stuff there? So let's see then. So the atom that should be larger is here going to be, and again, if we look at the periodic table, sodium's to the left, chlorine's to the right, and they are both in the same period. So we should know that sodium further to the left would be larger. So our sodium here should be our larger atom. Which should be larger. Lithium or cesium. So now we got two again in the same group on the periodic table, and we do have cesium being lower down in the group. So we should expect that cesium would be larger. Again, more protons and more importantly, more electrons. So got to put those electrons somewhere, right? We have more people, got to space them out somewhere. You know, if you're in a big crowded room, you're not going to be able to get to the front, right, with all those people. If you're in a room with only 3 people, you could probably get yourself to the front of the room. And it's sort of the same idea here when we're thinking about electrons and just the overall size, right? That's why when there's a lot of people, we say, wow, there's a lot of crowd going on happening there. All right, so why don't you take a second and think about these two things. Which is larger? Is it the hydrogen 1s orbital or the lithium 1s orbital? And which is lower in energy? Is it the hydrogen or the lithium?
Is it the lithium 1s orbital for both?
Almost. It's 50% right. So let's see which one that one is right for. Let's start with the first one. So which one is larger? Is it the hydrogen 1s or the lithium 1s? It is actually the hydrogen 1s orbital. And the hydrogen 1s orbital is larger because the electrons are not as bound to the nucleus. So what that means is if we think about the nucleus in a hydrogen, that's a +1 charge. And if we think about the hydrogen or the nucleus in a lithium, that is a +3 charge. So in both cases, we're talking about really the 1s orbital, right? And the electrons that are there. So as we talked about earlier, right, the size of the positive charge, right, will affect the attractive forces. So this hydrogen here has only a +1 charge. So this electron is feeling that +1 charge, which is a good attraction. But when we think about lithium here, it's feeling a +3 charge. So this electron in their first energy level is going to be pulled much closer overall. And we would expect this guy to be larger. And if we just think about sort of what's happening, right, on the periodic table, hydrogen is kind of below it, even though they're technically not in the same group. But again, as we go down, overall size should be sort of larger here, but this is the reason why the 1s part of it will be larger in the hydrogen, because it will not feel as strong as a pull in that case. So we can't really judge it here because they're really not in the same group. But this guy will pull it in closer. In terms of energy, the 1s here would actually be lower in energy, and it's really sort of for the same sort of reason. This is our 1s sort of region. So again, because of the larger positive charge here, it's going to bring that 1s orbitals closer to the nucleus and going to be lower in energy because of that, versus here where the 1s won't pull in as much because of that nuclear effective nuclear charge. Questions on that there? So here we want to arrange these in terms of increasing ionization energy. So when we look at SOF here, that is sulfur, I believe, oxygen, and we've got there fluorine. So when we look at the periodic table, we're talking about sort of this arrangement in terms of the elements, right? This is group 6 and group 7. So in terms of ionization energy, again, it increases as you go to the right and up, decreases as you go down. So we definitely know that sulfur here should be the least, right? It's below both of those guys. And we do have it increasing as we go this way. So in terms of increase in ionization energy, I think we're good with how it is worded there. SOF would be the correct sort of order for that. Again, sulfur being the least in terms of ionization energy because it's the lowest, and fluorine being the most. And in terms of atomic size here, we have FOS. So again, the reason for that is size, smaller this way and larger this way. So again, fluorine being the furthest to the right there. It's going to be smaller. This would be larger, and then coming down would be larger as well. So FOS there, which is what they have there, is the correct order. Question on sort of periodic trends or anything of that nature there. You do need to know those periodic trends. So obviously ionization energy, what it is, the trend on the periodic table, including first, second, third sort of trend. Electron affinity, what it is, the trend. Electronegativity, what it is, the trend. And atomic size, what it is, and the trend on the periodic table. And hopefully how that all relates to what we expect in terms of metals and nonmetals. Any questions on any of that there? So I think we sort of covered this in the earlier part here about the periodic table. And a couple of reminders. I think we covered it, but just to make sure everybody's again on the same page. The valence electrons is the outermost electrons, the ones at the highest energy level. And again, that is the same as the group number. So 1, 2, 3, 4, 5, 6, 7, and 8 is the number of valence electrons. Again, that's the easy way to figure it out. I think we also talked about charges on the periodic table. A reminder that everybody in group 1 makes a +1 no matter what the situation is. Everybody in group 2 will make a +2 charge, as I mentioned earlier. Group 3, which is really aluminum. And then group 5 on the non-metal side up above that staircase, which is coming down, -3, -2 for 6, and -1 for group number 7. Our transition metals, again, have a variety of charges. There's only 3 that have fixed charges, and I think we might have talked about them, but just in case, zinc and cadmium, when they do make a charge, always going to be +2 no matter the situation. Hang a left over there by cadmium to silver, and it will be +1. Everybody else in the transition metal region typically will have multiple types of charges or a variety of charges that they can make. And I think the rest of it is sort of what we talked about here. I think I kind of jumped these slides. Again, a reminder, that's sort of periodic table and sort of what we talked about. And as you can see here again, alkali metal starts with lithium, not hydrogen because it's a non-metal. And I think we hit all these guys here. Prettier pictures perhaps, and our alkali metals. All right, any questions on that? That is chapter 2, I believe. Yeah, so the question is why lithium's 1s orbital is lower in energy, and it has to do with the comparison between hydrogen and lithium. And again, lithium has 3 protons, which means its nucleus has a positive 3 charge, and hydrogen has this 1 proton, which means it has a +1 charge. And if this is our 1s electrons, for example, they are the n equals 1 level, which is closest to the nucleus, right? But they're not equally close to the nucleus because of the attraction that occurs. So this electron feels the full brunt of the +1 charge. So what it's going to do is really bring in that 1s orbital, let's just say hypothetically here. And that 1s orbital comes here. But now the same 1s orbital in the lithium is not feeling a +1 charge, but it's actually feeling a +3 charge. And as you increase the charge, like +3, +4 versus a +1 charge, it is much stronger when you have a larger positive charge. So what ends up happening is that 1s orbital in the lithium will actually feel a lot more of an attraction and actually, for example, drop down to there. And as you can see, it's closer to the nucleus and thus would technically be lower in energy. Even though technically they're both n equals 1, they're both on the first energy level. Because of that attracted charge between the orbitals and the nucleus, it's going to pull that orbital in. And again, that's why overall the size of the atom sometimes will obviously be smaller as you go to the right and up on the periodic table because of that higher positive charge and less electrons. It's able to bring everybody in. And that's sort of the idea here. The actual 1s orbital will feel a stronger attraction to the nucleus because of that +3 charge than that same 1s orbital would feel in the hydrogen because it's only +1 charge. So it's kind of like, for example, the magnet example. If you took like a super small magnet, right, and you kind of put it next to like a paper clip that may be originally sitting in the same location, maybe it just moves it a little bit. But if you took like the commercial size, Costco size giant magnet, right, and you put it in that same location, it's gonna grab that paper clip really quick, right? And it's because of that stronger positive charge that electron and that orbital feels from that positive charge in the nucleus. It's going to bring it closer in. And by bringing it closer in, what that means is that orbital now becomes lower in energy than the equivalent 1s orbital in hydrogen. Other questions on that? Okay. So that should wrap, I think. Yep, chapter 2, that's good. So chapter 2 is done. Congratulations. We'll just call it a semester at this point. Go home. Hey, we are home. Hey, that's good. All right, so that ain't bad. Bye. I agree. Bye-bye. I like it. We should have a quiz, I think. So we're going to have a quiz next Tuesday. Quiz will be on chapter 1 and 2. Why not? Let's do 1 and 2. Why not? That's good. It's electron configuration, some waves and stuff like that. So we will take it on Canvas probably through Proctorial. You'll need to use that. So again, I did put that practice quiz up there. So do make sure that you go through it. Again, as you get yourself sort of set up with that. And when you do that, if you could, camera view of you and sort of your work area would be great. If you could kind of arrange that, scoot back or whatever you need to do so you can kind of see what's going on. And again, take that practice one. It is worth points. And again, it's just going to be graded on completion. But it's more important just to sort of get you set up so that when we take something that's real, like next week on Tuesday, you'll be prepared to take it. We'll take it either at, we'll either take it sometime during lecture or we will take it during lab, at the beginning lab or something like that. I'll let you know maybe on Thursday. I'm still trying to decide which way to do it. It's on Tuesday on chapter 1 and 2. Yeah. I'll go with the 15th. I have no idea what day it is. I think it's still September. I'm not sure. But we'll go with 1 and 2. I don't know. I haven't been out in front of this computer screen in a long time. It will be on that. Normal sort of rules apply. You will not be provided any type of formulas, but any type of constants or conversions and stuff like that will be provided for you. So things like 3 times 10 to the 8, Planck's constant, those type of things will be provided for you. But something like E equals H times the frequency, you need to kind of know those sort of formulas and stuff like that. Any questions on that there? Okay. So we got that. And again, this actually does also conclude everything that will be on exam 1. And if I'm not mistaken, exam 1 is scheduled for 2 weeks from today. So exam 1, I believe, is scheduled for 2 weeks from today. That also means that exam 1 homework will be due at that day as well. So hopefully you're working through that. If not, make sure that you do. And again, exam 1 will cover chapters 1 and 2. And again, at this point, the only thing that you need to know from chapter 3 is what we just talked about today, what electronegativity is and the trend of electronegativity. So that's all you need to know out of chapter 3. And again, it mainly will be chapter 1 and 2. And again, the electronegativity part out of chapter 3 in relation to the periodic trends we just were talking about. Any other questions on any of that stuff there? Okay, so we'll talk about the lab here today. We are going to do experiment 3, I think is what we postponed to. So we'll talk about that at the beginning of lab. And since I was over here a little bit, why don't we start lab about 7:20-ish or so? Yeah, so we'll start in that ballpark and come through the lab link. That way we could all